this next segment here, I think, is one of the most fundamental pieces of physics that we do with vector derivatives. And it's a derivation I'm going to do for you in the context of mass, but it works for energy, it works for entropy, it works for momentum, it works for heat, it works for electric fields. It has so many applications. And effectively, when you do it for momentum, what you end up doing is deriving the Navier-Stokes equation, which we don't teach a lot in physics classes anymore, but with the resurgence of sort of complex fluids and materials and modern processing and technology, hydrodynamics has kind of seen a renaissance as a physics problem. And so there are more and more people that do that. And so this is kind of one of the key underlying ideas. And it really comes down to flux. And so let's look at the pieces. We start with a volume. And I'm going to do it in terms of mass. Okay? And there's an amount mass m in the volume. So if this is a small piece of volume dV, and there's some density, then the dm, the small piece of mass, is given by rho dV. And what we want to do in this problem, and it would be true whether this was momentum, electric field, heat, thermodynamics, entropy, energy. So we want to keep track of all the mass that goes in and out of our volume. And we want to write down, there's really three possible ways we can get mass in and out of our volume. Well, there's two ways we get it in or out, I should say. And there is one way by which we describe its change. So how do we describe the change of mass inside that volume in time? What would be the physics? What is the mathematical representation of the physical idea that the mass inside our volume is changing in time? There's enough silence. Talk to the person next to you. What math tool do you want to use to describe how much the mass inside this volume changes in time? So let me focus you a little bit. I'll name some math tools. We have integration, we have differentiation, and we have matrices, and we have e to the I theta. So how would we represent the change in mass in time in our volume? Derivative. That's what change in time is. When you see the word change, you better take a derivative. Now, what derivative tells us how the mass changes in time in the volume? The partial m partial t. And the partial derivative is key. Why is the partial derivative key? Well, more importantly, I'm looking at a spot in space. I'm looking at this volume, right? The mass can change, as we're going to see, at that space by it moving through space, right? So the total derivative, in a sense, with respect to time, will involve motion through space as well as changes in time at a point. But what I asked you about was the change in mass at that point in space in time. And that's the definition of a partial derivative. And you really want to understand physically, and from a physics point of view, why we care about partial derivatives versus total derivatives. And that's one of the key reasons. Now, we're going to write it in terms of density d rho. So what we're going to worry about is d rho dt times the element dv that's not changing, right? We've picked a fixed spot in space that's not going to change, and mass will change if the density changes in there, because we're going to keep dv fixed. Now, so I'm going to rewrite that for you. So that's basically, no, that's still basically dm dt. It's just written in a slightly weird way. Now, So this tells us the change in mass in our volume. How can that mass change? If I have a volume, how can the mass inside my volume change? Okay, so I can stuff flow in or out, which is what? Flux. So we've already defined flux, okay? And mass flux will be the density that flows. So this really is a velocity here. And that'll be dotted into dA for the surface that it goes around. And now we have to be a little bit careful, right? We said stuff flowing out of a closed surface is positive. If the stuff flows out of a closed surface, what does that do to the mass? It decreases it. So we need to put a minus sign in by hand because of our definition of flux. Now you might read, some places depending on what they're doing, might define the flux as going in as positive, and then you wouldn't have the minus sign. But that's the more convention. Now, with mass, we do have a law. What's the law? Conservation of mass. However, you could imagine a nuclear reaction, right? We've learned that mass and energy, right, can be converted. And if we were thinking about other things like electric field, is electric field perfectly conserved? I mean, if I have a box, if I have a point charge, do I have electric field being created? Yeah, so we can have sources for that. If I have heat, I can have sources. Depending what I'm doing, we have to take into account the fact that there might be some source in the volume. So looking at this, what I obviously want to do is combine things together. So I'm going to bring the source term for now over here with the d rho dt. And I'm going to do what we've always done, is I'm going to add up all of our little pieces. So we've turned this into an integral equation. So notice we've used some key fundamental math ideas, and we've derived a very general equation. And this is what it means to build models, to build equations. We don't do it a lot in undergraduate physics courses. We tend to give you the models outright, or maybe we derive it once in class. But this is such a general way of deriving a model, I think it's critical for you to get. We think about the definition of the partial derivative in time, and that gives us this term. We then move over here, okay, and we think about the definition of flux, and that gives us this term. And then we think about the creation. We've just thought through all the physics. There wasn't really math. We thought about physics, and we converted physics into the key math terms. That is what we did. And then we ended up using our fundamental other idea of math, is that I did it for a small piece, and now I add up all my small pieces, and that's what integrating is. So I really like this because it pulls these together. Now, integral equations are nasty. We tend not to like them. We occasionally have to solve them. What can I do magically to this equation? What do I immediately see? And I should have been a little more clear. Since I have a volume, when I add up all the surface pieces, it's a closed surface. So what can I do here?
Do the easier one?
So talk to each other. What would you do to this? Chat. So what are we going to do next?
Divergence.
Why?
Because it's a scalar.
Well, yeah, so we're going to do the divergence. But what do we know? If we're integrating over the outside, the boundary, then we can turn it into an integral over the region of the derivative. And that's a little bit easier than trying to turn this into some integral over the boundary, because we got to like do the inverse derivative. It doesn't make real sense. The volume doesn't enclose anything. So the easiest thing to do at this point is rewrite this of the divergence. Now, notice I'm being very careful. I never said the density was constant. So we have to be careful and put the rho inside. Okay. Now, having done this, and this is our next key physics math idea that you will use over and over and over. So not just in this derivation. If I'm doing some integral over the same two volumes of something that's a function, unless random, really miraculous chance happens, that means the two pieces inside have to be equal to each other everywhere. Because if they're not equal to each other everywhere, the odds of the two integrals coming out the same, it's just not going to happen. It's certainly true if they are equal to each other everywhere, then the integrals come out the same.
Where did the psi go?
It's right here.
But I mean on the...
I just moved it from over here to here because it was a dv. I put all my dv's together and all my da's together. So if I go back up, right, this was a dv, so I moved it over to that side with my other dv.
Yeah.
And it's still there.
But in the second one with the
You changed it
divergence.
from areas and
Where did what side go?
On the right equation now, so on the left side we have psi, partial d
Right.
equals, and then it's the
Equals rho v dot dA. And now I have the divergence of rho v.
yeah. And why isn't there a psi term there?
Because then why would I have a psi on both sides? There's only a psi on one side. There's no psi here,
Oh. Oh, okay.
right? It's moved over there.
You just dropped that. Oh, got it. Never mind.
Yeah. But now I can pull these out and I have d rho dt, and I'm going to reorganize this, plus grad dot rho v equals psi. So I brought that over there and the psi over there. And this is the continuity equation. And one of its more common forms is, like we said, with mass in general, there's no source for mass, right? So if there's no source terms, then we see d rho dt plus grad dot rho v equals 0. And I mean, the divergence. So basically, the divergence of rho v is telling you whether or not the mass is changing inside. And remember, divergence told us about whether stuff comes in or out. And what we find for fluids is a very interesting case. If rho is constant, right, then d rho dt by definition is 0. I can take the rho outside of the divergence because it's a constant, and I get del dot v equals 0. So we see for fluids with constant density, right here we're learning some interesting physics. Then del dot v equals 0. So one of the things that vector fields for which del dot v is 0, they're often called incompressible. That's just a word that's used. Okay. They're also, like I said, irrotational, and there's other names for them. Oh, not irrotational. I take that back. That was the curl. Sorry. But this is, they have a vector potential. There's no net flux, other things like that. But incompressible is a big one. And this is not just a velocity mass thing, right? I could go back and do this for any type of system I want. You have to be a little tricky if you're going to do things like do this for momentum, then you find you have to be a little fancier here, and you really have to worry about tensors, because the momentum flux is a tensor, because you've got the momentum itself moving in a particular direction. And remember what we said, tensors are fundamentally things when you have two directions. You have the momentum with the direction, and then the surface direction that it's moving through. So you end up with a little more fancy stuff, but you basically get the equivalent of a divergence acting on a tensor, and it all works out. So this is such a fundamental key idea that I can't emphasize enough. Let me just quickly say it. We pick out the key physics using our partial derivative in time. We track how that actually changes. Notice I wrote down this equation by translating words. You know, it wasn't like I invoked Newton's law. It wasn't like I invoked energy conservation. I just literally kept track of what was happening and turned it into the right differential equations. And then from there, I summed over my pieces. I used my integral theorem to change my integral. I then used the fact that everything under the dv means I get to pull out the differential equation. And I end up with a fundamental differential equation to describe the system. So it's a great example of model building, using all our math ideas and bringing it all together. Just to give you an idea what we have left, I do want to prove, or slightly prove for you, the divergence and the curl theorems. We've just used them for now, using our general idea. I want to show you where they come from. Those are useful proofs to see. We're going to do a couple of examples with those, and then we'll be done with that. And I think we can get that all done next Tuesday. And then that'll leave the last week to do a little bit with PDEs.